Hi there, it's Mrs. Trombley. It's time for lesson 6-4, and it's finally time for exponential functions. No more straight lines. We have graduated straight lines. Well, I guess we've never officially will get rid of them. That's actually some built into this lesson too, but something new, something exciting. No more y equals mx plus b. Now it's y equals ab to the x power. I know, exciting. In this, a cannot be 0, because if a were 0, then 0 times anything is 0, right? So y would just be 0, and there would be no exponential growth going on. B also can't be equal to 1, because if you raise 1 to a power, it's always 1, isn't it? That's not going to be exponential growth, it's just 1. B has to be greater than 0, though. So a number greater than 0, but not 1. So in all this, the y represents the amount after x time periods. That makes x the number of time periods, yeah. A is the initial value, the starting point, also known as the y-intercept. Yep, so whatever number I'm multiplying by that b to the x power, that's how you identify the y-intercept. This b right here, that's the growth factor. So instead of a constant rate of change, like in slope, where it's the change in y, change in b, we're looking for what number's being added each time. I'm looking for what number's being multiplied on the y every time. That's how you find your b. So the growth factor is the multiplier, the common ratio. It's the word factor, so we know it's something that you multiply. All right, we're going to look at how to identify exponential functions from a table. I've already shown you the equation. I want you to be able to graph an exponential function, and I also want you to be able to write an equation from a graph. So that's our goal. Pretty lofty, but I know that we can do it. So let's ride. Okay, so identifying exponential functions from a table. In an exponential function, the dependent variable, y, increases by the same multiplier. So we're not adding the same amount every time. We're multiplying the same number every time. And the independent variable, it's still increasing or decreasing by a constant amount that's added or subtracted. So you don't have to multiply on both the top and the bottom. It's just the bottom, or just the y, the dependent, or on the right side if it's written vertically. That one's the one that's being multiplied. So what I ask you to do here is to tell whether each table represents a linear or exponential function. So you have to determine which one is it. Then I want us to be able to write an equation that represents each table, because yes, I do want you to be able to generate an equation from a table, and you'll see that with exponential, it's pretty easy peasy. So let's go. All right, let's take a look and figure out if there's a constant rate of change or if there's a common ratio going on. On the x, 0 to 1, 1 to 2, 2 to 3, I'm sure you're saying, hey, I'm adding 1 every single time. Here, I know that 2 plus 2 is 4, but 2 times 2 is 4 too, so, I don't know. Well, 4 plus 2 is 6, and 6 plus 2 is 8. So I'm adding the same amount every time. Multiplying the same amount doesn't work, right? Because 2 times 2 is 4, but 4 times 2 isn't 6. It has to be the same every time. So this is a plus 2. This means, yup, it's the linear one. So go ahead and write linear. And let's review. How do you write an equation? Well, I know it's in y equals mx plus b form because I can eat, breathe, and sleep and dream about it. That form. So y equals slope, change in y over change in x. So that would be 2 over 1, which is 2. And the b, that would be the y-intercept when x is 0, y is 2. So there, we've done a little review. All right, take a look at letter B. Same thing, let's look for the change. 0 plus 1 is 1, plus 1 plus 1. So we're adding 1 every single time here. On the bottom, 4 plus 4 is 8, but 8 plus 4 is not 16. So that one's not linear, I know that. Let's see. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. Yeah, I'm multiplying by 2 every single time. That's what I mean by growth factor. It's the same amount that's being multiplied every time. By the way, if you didn't know that 4 times 2 was 8, you can figure out what number you're multiplying by working backwards with division, right? So if I don't know 4 times what is 8, I do know that 8 divided by 4 is 2. And I'm not telling you this to insult you, I'm telling you this because sometimes you're not going to have one that jumps out at you like this. So if you're ever wondering to yourself, well, this number times what gives me the next one, just divide the second by the first and you'll get that factor that you need. All right, so this is exponential. And remember, we now have to write an equation. Okay, I know it's going to be in the form y equals ab to the x. And you have a little list up top in these notes that tell you what's what. Y is what we're solving for. And what's nice, y and x, they always stay letters. Just like before, the a and b are what we're figuring out here. So it says up top that a is the initial value, the y-intercept, the amount you start with. There it is. So a is 4. I'm going to write that down. I'm supposed to multiply a by b to the x power. B is the growth factor. Our growth factor is right here. Every time we're multiplying by 2. That's the factor. I'm going to wrap that in parentheses because that's how you normally see it, and raise it to the x power. That's your equation. There you go. All right, next, another table here. Let me make sure you can see it. Yep. All right, so this time it's vertically, so you don't think all tables are written horizontally. -4 to 0, 0 to 4, 4 to 8. Yep, we're adding 4 every single time. To get from this y to this y, okay, I know that 1 times 0 is 0, but 0 times 0 is not -1, so this isn't going to be exponential. 1 plus -1 is 0, and 0 plus -1 is -1, and -1 plus -1 is -2. So we're adding a -1, or maybe you just look at it as subtracting 1. Both ways are correct. So there's a constant rate of change here. That's linear. For our equation, y equals, to get my slope, it's the change in y divided by the change in x. The change in y is -1, the change in x is 4. So I've got -1/4 x. And the b is the y-intercept. When x is 0, y is 0. I don't need to write +0. That would just be silliness. So that's it. Done. All right, last but not least, with our tables, I see in the x's 0, 1, 2, 3. Yep, it's going up by 1 every single time. And I know that 8 minus 4 is 4, but 4 minus 4 is not 2. So I'm guessing this is exponential, but having a hard time with 8 times what is 4? I know, right? Why couldn't it just be a 4 and then an 8 after it? Because that's just like the other one that's pretty simple. I know that we most of the time think in whole numbers, but I can multiply 8 by something to get 4. Remember how up top I said if you can't figure out 4 times what is 8, you can just take 8 divided by 4 to get that? Same thing here. If I don't know 8 times what is 4, well, what's 4 divided by 8? Yeah, it's a half. It's 0.5, 5/10. 8 times 5/10 is 4. And 4 times 5/10 is 2. And 2 times 5/10 is 1. So as long as b is greater than 0, we're okay. And 5/10 is greater than 0. This is exponential. So we'll go ahead and write that down. Exponential. For my equation, yes, it's y equals. So it's y equals a, which is the initial value. So when x is 0, y is 8. Times the growth factor, which every time, 5/10 to the x power. And we have an equation. Nice. All right, the next thing I want you to be able to do is to evaluate exponential functions for given x values. And this is just to make sure you are calculator savvy here and entering these in the right way. So if you don't have your calculator, you're going to want to have it. Please get it. Press pause. Welcome back. Hi, hope you have your calculator in front of you. Okay, so here I'm just asking you, hey, when x is 3, what's the value of y? So all you're doing is taking -2 times the quantity of 5 to the 3rd power. That's what you're going to enter in. So when you're entering that in, remember that you just need to use that little caret top button for the exponent, that one underneath the clear, if you're using this calculator. So I would just type in for that one, -2 times the quantity of, and I would get in the habit of using parentheses. Wrap your b up in parentheses. And I'm going to use that little caret top button and the 3. Yours might say caret top 3 instead. When you hit enter, it gives you -250. That's it. That's what evaluate means. So you're telling me what y equals when x is that given amount. So maybe try the next 2. Hit pause and then see if you got it right. Or not. So maybe you hit pause and welcome back, and if not, all right, I'll work through these with you. This is my equation. So I'm trying to figure out what's y when x is a -2. So in my calculator, I'm going to type in 3. I'm going to wrap up 5/10 in parentheses and raise it to the -2nd power. And you should get, drum roll, 12. If you didn't get 12, try entering it again. Hit pause, go back, try to enter it again. Last one, maybe you don't want to use your calculator for this one, because take a look. This is what I'm evaluating here. Order of operations says to do exponents first, right? Well, what's 2 to the 0 power? It's 1, right? What's negative 4 times 1? Yeah, it's negative 4. Wasn't that faster than typing it in? You could type it in to double check, but try to, every so often, let the calculator be free for a while. Save its batteries, conserve. All right, flip the paper over. No, we're not done. Remember I said we had to graph these things? Yeah, I know. All right. Now you are going to want to use your calculator for sure. Let me zoom out a little bit here. Okay, graphs of exponential functions. I know that you have seen these. We did a little calculator lab with all of this. Hopefully I didn't run out of time, and we still did the lab because it's a really good one. And you've seen that the graphs of exponential functions are kind of curvy. Yep. To graph an exponential function, all you need to do is make a table of values and plot the ordered pairs. Then you're going to join them to form a smooth curve. So you don't need a ruler for these ones, but your calculator will prove to be helpful. All right, so I ask you to graph each exponential function, and then I want you to list the domain and the range. Yep, both. Remember, domain tells me what x can be, and the range tells me all the values y can be. It's been a while, I know. Okay, so I said step 1, make a table of values. Okay, so basically we're going to do what we just did on the other side when we plugged in values for x to get y. So let's start off with a lovely one. When x is 0, you get to choose the x values. It's independent, and y happens. Y depends on what you get for x. So when I have 2 to the 0 power, I plug 0 in for x. 2 to the 0 power is 1. If I plugged in 1, 2 to the first power would be 2. If I plugged in 2, 2 squared would be 4. If I plugged in 3, 2 to the third power would be 8. If I plugged in 4, I'm going to get 16, and I don't have enough room, so I'll stop there. I wouldn't mind getting a negative value in there to see what happens. So let's try negative 1. Remember, when you have 2 to the negative first power, I put it through the car wash, so it's really like 1 over 2 to the first power, which is 1/2. So when x is negative 1, y is 1/2. We're going to plot those values now. All right. So when x is negative 1, y is 1/2. So on my x-axis, I'm going to go negative 1, and then I'm going to go up 1/2. When x is 0, y is 1. When x is 1, y is 2. And when x is 2, y is 4. And last but not least, when x is 3, y is 1, 2, 3, 4, 5, 6, 7, 8. You can see it's kind of a curve here. Okay, now you might be thinking, okay, well, how far down does this go? Well, you learned from your calculator number that the number being added here kind of tells you where this graph stops. So what could I write? Plus what? Wouldn't this be the same as saying plus 0? So this right here, when I'm trying to figure out how far this extends this way, it can get super duper close to 0, but can never touch 0. So when you're doing your graph and trying to extend it in both directions, just make that line get pretty close to the 0, but don't let it go past it, and don't let it touch it. Do the best that you can. So there's the curve of it. That's what it looks like. Now I also asked you to give me the domain and the range, right? So remember, domain, that's telling me all the different values that x can be in your data table on this graph. And there's an arrow going here, right, that's going to keep going and going and going. So x can extend infinity this way. And I know this is pretty steep, but it's going to continue to get farther and farther over. And this line goes on forever. That means that your domain, the x values, can be anything. They can be all real numbers. So I'm going to use that fancy R. As far as the range goes, remember I said that this line can get super duper close to the 0, but it can't touch it? If you're looking at the y values, I said y can't be 0, right? Because it can't touch that. but can't it be any value that's greater than 0? I can get to the point on this line using any value of y greater than 0. So all we have to do to write a range is say, okay, y is greater than 0. Can't be 0 though. All right, take a look at the next one. This time I'm going to show you my shortcut. We're going to kind of cheat a little bit. I guess it's not cheating if I'm telling you you can, but instead of taking the time to generate my own values in the table, I do want you to be able to generate your own, and that's why we did the other one the way we did it. But you know that you can also just press y equals on your calculator. So if you don't have your calculator, maybe hit pause, go grab it, because I want to make sure you know how to do this. Welcome back. Go to y equals, type in that equation, and I can get my table of values, right? All we have to do to get the table is press second graph. Now, I have a big table of values here. I can choose some friendly numbers to use based from this. So I know it's kind of hard to see what these values are with the glare here, but I want to include some negative values. So you can see when x is -1, y is 3.5. So go ahead and write that down on the side. I do still want to see your table values, so if you happen to get it wrong on an assessment, I can understand why. Alright, when x is 0, I see that y is 4. When x is 1, y is 5. When x is 2, y is 7. And basically plot as many points as you can fit on there. With exponential growth, usually it's like 5, and that's about it. When x is 3, y is 11. And when x is 4, y is 19, we're not going to be able to fit that on here. And if we keep going backwards this way, the numbers are just going to not be too different from one another. They're just going to keep getting smaller and smaller and smaller as they approach 3, but never touch 3, because this right here tells me, all right, that's where my y is happening, where my range is. Okay, so let's plot these values. When x is -1, y is 1, 2, 3.5. When x is 0, y is 4. When x is 1, y is 5. When x is 2, y is 7. When x is 3, y is 11. 8, 9, 10, 11. Okay, again, we see that this 3 is being added. This line can get super duper close to 3 on the y-axis, but it's never going to touch it. Can't touch this. Boom, 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 boom. I hope you know that song. If not, I don't know. You have to hear it. I'll wear my t-shirt that talks about it. You'll see. Alright, so there we have it. It's a nice curvy line. Now we still have to list the domain and the range. Domain, range. So again, as far as x values go, I can get to any point on this line from any real number, because these arrows mean it's going to keep going, and anything goes. That's a musical, isn't it? Alright, all reals. As far as the range goes, remember, as far as y is considered, or y, yeah, looking at y can't be 3, but it can be any value greater than 3, so I'm just going to say y is greater than 3. Why? Because right there it says so. Okay, so that's that. Use your calculator to help you out, but no, for some of them, like the 2 to the x, why bother typing in a table? That one's pretty easy to figure out. But in general, I would use a calculator to double check it. I want you to know how to do it both ways. Okay, last little portion here, and then a math story. I'm going to give you a graph, and I want you to be able to generate an equation from the graph. So you know how to generate graphs from equations, and you know how to generate equations from tables. Now I want you to be able to look at this and give me an equation from it. So this is about bacteria. Bacteria are a prime example of exponential growth. Yes, exponential growth is what I call it. Ha ha ha. All right, anyway, sorry, I'll stop. The graph represents the bacteria population Y after X days. Remember how I said that X represented time periods? When you put a situation with it, this is usually the case. So I want to know the total population Y after X amount of days. A, write an exponential function that represents the population. So I'm asking you to write me the equation. In order to get the total bacteria population, what would my equation be? Well, you learned how to figure this out from a table, right? And a table is just made up of ordered pairs. So let's use our ordered pairs to help us. I know that y equals ab to the x power. A is the initial value. It's what y is when x is 0. You're told right here that when x is 0, y is 3. So that means that A is 3. That's my y-intercept. So far, so good, I hope. All right, now, B, I'm going to wrap it up in parentheses. Why not put my little x there right now, because I know it's going to have to go there. Now I need to know, on my y values, on my dependent, what is my multiplier? So take a look at these y values. I go from 3 to 12, and then let's see, from 12 to 48, from 48 to 192, from 192 to 768. What number am I multiplying by every time? Well, 12 divided by 3 is 4. That means 3 times 4 is 12. 12 times 4 is 48. 48 times 4 is 192. So that makes my B 4. We just generated an equation. So just look at these as ordered pairs. Look at those ordered pairs as points in a table. All right, now letter B says find the population after 12 hours. Okay, so remember the second part, we had to learn how to evaluate. Well, now I'm telling you an amount of time. That means I'm giving you a value that I want you to plug in for the x. So I'm going to say y equals 3 times the quantity of 4 to the. Now you might want to plug 12 in here, but see up here how it says x days, and this says 12 hours? You can't plug 12 in there. How many hours are there in a day? I wish there were more, but yes, there are only 24. So what I'm really going to plug in here is 12 divided by 24. Or some of you just said, well, hey, that's half of a day. Ding, ding, ding. That is right. I'm going to put 0.5 in for my exponent. So be careful. Make sure the units match up. So try that. Take 3 times the quantity of 4 to the 5/10 power. I'll do that in my calculator so I know I'm giving you enough time. I've already done it, but there we go. All right, and hopefully you got 6. So y equals 6. So that's not too bad. After 12 hours, there's only 6. But now it says find the population after 5 days. And then we're going to learn why it's exponential growth. Okay, so 5 days. Y equals 3 times the quantity of 4 to the, and now the days match the days, right? So now try this again. Type in 3 times the quantity of 4 to the 5th power. What did you get? Did this number gross you out? Kind of grossed me out. 3,072 in 5 days. So starting off, half of the day it's only 6, and then 5 days later, 3,072. That's kind of growing pretty fast. Yep, it's like a rumor in the middle school. Yes, I am familiar. They grow really, really fast. That's exponential growth. All right, math story time. It's the best time. It's the most fun part of the notes. Again, it's about bacteria. A bacteria population y after x days can be represented by an exponential function whose graph passes through. So what I did right here is I gave you 2 ordered pairs. Or you can even look at it as I gave you 2 amounts in a table. Sometimes looking at it that way is helpful. That's what those are. This is x, this is y, this is x, this is y. Write a function that represents the population. Okay, if we're going to write a function that represents the population, then I need to know my initial value a. I need to know what's y when x is 0. And you're told when x is 0, y is 100. So that's my a. To find the b, I need to know, okay, what do I multiply the first y by to get the next y? Well, 100 times what is 200? You guessed it, 2. So I'm going to put my 2 there. And if you didn't know, take 200 divided by 100 and you get 2. And since I'm just writing the rule, I'm going to put an x in there to represent the number of days. So there it is, initial value, multiplier. Those are the only 2 things you have to figure out. Letter B says find the population after 6 days. I'm asking you to plug in days for the variable that represents days. So y equals 100 times 2 to the 6th power. So how many bacteria will there be? Type in 100 times the quantity of 2 to the 6th power. Yeah, it's pretty gross. Yeah, 6,400 bacteria. I hope you enjoyed your lesson. I'll see you tomorrow.